Okay, thank you so much. So yeah, today I wanted to talk about a topic that I've spent quite a bit of time working on, namely continual learning. And I just sort of want to phrase why this is an interesting problem, and yeah, what can it do for typical machine learning in general. And just a few words about myself. So I'm currently a research scientist at DeepMind. Before that, I did my PhD in Montreal, working with Professor Yoshua Benjo. And as I mentioned before, I'm sort of originally from Romania, where yeah, cool. So let's sort of jump into the talk directly. So I wanted to start with a little bit of motivation for continual learning, and I guess sort of the tagline that people usually use when they approach this problem is sort of this idea that the world is non-stationary. So briefly, what that means is that you know, whenever we do machine learning, we tend to work with a fixed data set where everything is static. We train that system, we evaluate that system for that particular data set. But then when we deploy the system, we need to interact with the world, and the world keeps changing, right? So the distributions that the system will need to face while interacting, while being deployed, will change over time. And you know, there are many examples. You can go from language, where like new words keep emerging all the time. So for example, in 2020, we had the word COVID that became extremely popular in the news and everything. And language models that were trained prior to that would basically don't have this word in their vocabulary. Or things like robotics, where you have tear and wear, where you know, even the robot itself, the way it reacts to the commands that you give to it changes over time, or things like health, right? And just to reiterate what I said, sort of deep learning works really well, but what it really does, it's sort of just a very powerful tool that can work with big data sets. So it expects you know, everything to be fixed, and it relies on lots of different ways to kind of be able to work at the scale and parallelization and so forth. But fundamentally, it relies on gradient-based optimization, which requires an IID assumption. So the way optimization works in general, it requires this IID assumption. So it requires everything to be static, and for you to be able to sample IID from it. And this is sort of different from how the world works, and maybe even from how we as humans work, right? So actually, humans are really bad at learning in an IID setting. So sort of imagine you know, you need to learn for your exams, and then you have to like randomly sample from different topics, right? You read a sentence from the math book, and then you jump to geography or biology, and that's just impossible. And if we are like a big goal in machine learning, many times tends to be sort of our desire to imitate or to get closer to sort of human intelligence. And Thurman Griffiths has some really interesting work on this topic, and some interesting thoughts on it. So in this particular paper, Understanding Human Intelligence Through Human Limitation, he argues that actually sort of the way our intelligence behaves and exists depends on the limitation it has. And sort of this kind of just, again, highlights the fact that what we're doing now with machine learning, it doesn't seem to go in the same direction with how like human intelligence behaves, just because it has very different constraints and very different protocols and paradigms in which it works, right? So the fact that humans learn in a continuous way from highly correlated data is somehow affects sort of the kind of solutions we find, and it potentially is impossible for an ML system to reach to similar solutions without working in the same setup. So the way, as a research problem, the way this is being formulated is through the continual learning or other, you know, again, as many times in the research community, you have sort of many subfields that are very heavily related. So I guess continual learning, lifelong learning, they're extremely similar. So you can use either term, whichever one you like. But in general, this definition is a very pragmatic one, and it's usually done by defining a protocol, right? So when we want to define continual learning so that we can try to study systems that learn in the setting, we talk about sort of the setup. We say, okay, you know, we will have a sequence of tasks. You'd have to go over them one after the other. You have to keep learning, and then we have different variants of how this sequence of tasks might happen. We might have smooth task transitions where you kind of blend from one task to another, where you can have very sharp transitions where, up to point T, you do task 1, then you suddenly do task 2. You might have repetitions of tasks. You might have that every task is unique. The tasks might have different types. We could talk about unsupervised, supervised, semi-supervised, RL, whatever you want, but like different kinds of objective, different kinds of outputs, right? They might not live in the same space. You might not even have tasks at all, right? It might just be a continuous stream of data that changes somehow in an interesting way. So that's sort of the first half of what you need to do when you start defining continual learning. So you have to define the protocol and what is that you have to deal with. And the second part is, what do you want from a system that is able to solve this? And usually this comes as a list of desiderata. So, people would say, okay, I'm training the systems, and what I want to do is I want to have a system that once it learns task 1 and it goes to learn task 2 and 3, it still remembers the solution of task 1. So this is usually, not suffer from catastrophic forgetting. A second desiderata that we typically ask for is that we want the systems to learn faster and faster, right? So we want the system to show forward transfer because, task K and task 1 might have something in common, so you want to exploit that. So when I hit task K, I want to start learning faster because I have this prior knowledge that I've acquired at some point in the past. And so this will be forward transfer, or you want to have backwards transfer, which goes sort of the other way around, which says, okay, if task K and task 1 have something in common, and now I'm learning task K, I somehow want to improve on task 1 as well, because I'm learning some skills that would be useful for task 1. So if you put me back in task 1, I want my performance to increase. There is this concept of plasticity, which means that the system can keep learning. And there's also restriction on model size. And this is particularly when you're thinking about a lifelong learning scenario where you're going to have hundreds of tasks that you have to go through. If the amount of compute that you need to do inference or even to do learning increases with the tasks and increases in a bad way, like, I don't know, quadratic or exponential or whatnot, then this will become very quickly prohibitive to you. So what you really want is a system that doesn't need to pay an additional cost, a computational cost or memory cost or model size cost. I think there are different axes and different people care about different care about combinations of this, but ideally you want the model to a certain extent to stay constant, or at least the computation to stay constant. And I wanted to add a note on the plasticity, so in this ability to learn, because it's sometimes kind of a bit tricky, and I just sort of want to clarify what I mean by that. So there are potentially 3 things that people can think of when they think about plasticity or the ability of the system to keep learning. So the most traditional thing that people have studied in the past is sort of this idea of forward transfer. And in forward transfer, what we really mean is that we want that if task 1 and task 2 are related, we want that when we learn task 2 to start learning faster. So it's all about speed of convergence, right? So the assumption is you will be able to learn task 2. That's not a problem. The only question is, are you going to learn it faster, or are you going to learn it as slow as if you haven't seen task 1? And this is sort of what people usually cover under forward transfer. Another potential problem that comes into play that was described in Chaudhary et al. It's called intransigence, and this is the idea that you're unable to optimize. So what might happen is, because you've learned task 1, you're now at a particular initialization that makes it impossible for HGD to learn anymore. And you kind of get stuck. So you can't get training error, test error go down. And I think this is sort of a very interesting question as well for optimization perspective. But the last thing, and this is sort of slightly new, and I think something people haven't paid attention that much, is this idea that you might be actually losing the ability to generalize. And for those who are kind of interested in kind of quirky ML problems, I would suggest for you to look at this paper from Jordan Ash and Ryan Adams, where what they show is that if you train on half of CFAR and then you fine tune on the full CFAR, you can't generalize as well. So basically, you can't get the same generalization. There's a generalization gap that appears. In both cases, you get to get your training error to be 0, but you can't get the same generalization. So it seems that somehow pre-training affects your ability to generalize in a way that we don't want. And this can be very problematic in a continual learning setting where, as you go from task to another, if you lose this ability to generalize, you basically lose the ability to learn meaningful solutions to future tasks, even though you can reduce the training error that you see for any future task to 0. Okay. And I guess the main point and the main issue why continual learning is so hard is because the way it's defined is through this list of desiderata, and they tend to be contradicting each other. So once you start playing in this space and you start trying benchmarks and you start trying methods, what you realize is that what we actually after is some kind of trade-offs. We know we cannot maximize all of these different things at the same time. And we need to, pay something to get something. And the question becomes, what is this optimal trade-off that we're after? And this is sort of a really hard problem. And it's a hard problem because most likely there is no one trade-off that we actually care. So depending on the setting that you're in and depending on what you're trying to do, different trade-offs make sense. This kind of emphasizes the need of having like some real-world problems that we might want to tackle right now, because it seems that the data itself like imposes the trade-off that makes sense. And I think this has been a continuous issue in the field, is the fact that we've been working a lot with benchmarks and with algorithms that are developed for these benchmarks, and we're kind of solving and we can finding certain trade-offs that might not be meaningful in the end, and there's sort of just a continuous tension in the field. And it kind of boils down to the question of like, okay, what do we want to use this continual learning system for? So I gave you initially like a grand scheme motivation, and about human intelligence and how humans learn, and the world is non-stationary and so forth. But then like we can't really go directly for that problem because there's no way for us to test our systems in that kind of settings. So the question is, tomorrow, if I want to use a continual learning system, what is that pragmatic problem that I might want to go for? Or what is the reason I'm trying to do sort of the research in this space? Okay, sorry, just going to the next slide. And I've tried to list sort of the reasons that you or anyone else might come for trying to deal with this problem. And there are many reasons that make sense, and there are many settings that you'd want to use this. But like for me, I do like sort of this angle that the data is really important, and I do like sort of the idea of us coming up with the real benchmark that we care about. But for me, it's also like, and I want to kind of highlight this, that there are other ways to solve this contradiction between the different ones of CL, and that's kind of just changing your perspective of why you're doing CL. And I've highlighted this particular one point that I'm particularly interested in right now, which is, for me, CL, it's the study about how we can accumulate knowledge in a way that's reusable in the future. So for me, CL is sort of this idea of us building on the knowledge that we have and being able to learn and use it to learn more efficiently after that. And what we can do is we can, even in toy domains, we can check whether the mechanisms that we have allow us to do any of that. And to kind of go a little bit more in detail of what I'm thinking, I want to present. So some of you might have already seen this, but I like thinking a little bit about sort of what the ID assumption for gradient descent is, and how sort of this plays into continual learning and in sort of this theme that I'm trying to build here. So gradient descent, gradient-based optimization is something everyone probably knows. It's a very fundamental algorithm that's been with us for more than 4 decades now, and it's what everyone uses. But it always makes sense to go back to the basics and try to sort of reason through how these algorithms works and what they do. And one way of thinking of what gradient descent does is, well, you're basically independently for each parameter, you're asking a very simple question, which is, if I increase this parameter or decrease it, what would happen to the loss? Would the loss increase or decrease? This is basically what the derivative is, right? Like what would happen to the loss if I add an epsilon to the parameter? And you're asking this question independently for each example in a mini batch. For example, when you're doing mini batch of GD, and you get different answers, right? So some would say, it needs to increase. Some would say it would need to decrease. And you can think of this as a sort of as a tug of war, where each example is trying to pull of the parameter in one direction or another. And the way learning happens is you have all of these examples trying to push the weights towards themselves, and you reach some kind of equilibrium at some point. So you're playing out this sort of tug-of-war game, and you get some kind of equilibrium, and that's how learning happens. So what does that mean, and what implication does this have for learning? So what that means is that for learning to progress properly, you need to have, at the same time, or at least in expectation, you need to have all the examples present, right? If you're playing this tug-of-war game in order to learn, for the tug-of-war game to make sense, you need to have everyone that's supposed to play the game needs to be there pulling on the rope. Otherwise, the result will not be meaningful. And what would happen in a normal learning system is that actually not all the examples that we're learning are equally hard. Or if you're doing multitask learning, not all tasks are equal. So what might happen is that early in the learning process, you'd learn a big chunk of your data set, so you'll be able to perfectly predict sort of what is the right output for many of your examples. But because you have to enact this tug-of-war game, you still need to evaluate those examples, and you still need to compute the gradients of those examples. So like if I'm learning ImageNet, and I would say in the first step of 50% of the data I'm classifying correctly, if I'm throwing that 50% of the data out and just learn on the hard examples that are left, what would happen is, well, that part of the data, that mode of the data is not going to be present in the tug-of-war, and we're going to forget it. Catastrophic forgetting kicks in, and what would happen, you learn the hard ones and you forget the easy ones. And this is sort of how we lose a lot of learning efficiency and a lot of computational efficiency and potentially even data efficiency through the fact that, in order for learning to happen, we need to have everything present at the same time in order for HGD to make sense. And what is even more interesting is, we have sort of this understanding that there are easy and hard examples, and this is sort of what happened. And there are multiple papers that are looking at this for particular data sets, and always show that any data set has this bimodal distribution of easy and hard examples. But there is even new evidence that even if you do, say, even if you have tasks that are equally hard, you still don't learn them at the same time. So this is actually quite an interesting result that I'm going to go talk a little bit more about it on the next slide. But basically, the outcome is that in learning, we learn modes of the data sequentially, but because of this tug-of-war dynamics of HGD, we need to have all of them present at the same time. So we're paying a huge computational cost. So what a solution to continual learning or a solution to learning things sequentially can do, it can help you get this sort of learning efficiency. You can get unprecedented learning efficiency by avoiding repeating things that you've already learned, by allowing you to focus only on the things that you don't know and sort of keep learning those. And then to me, this is sort of a promise of continual learning that I think goes beyond the world is non-stationary and can sort of have an effect on all forms of machine learning that we're doing right now. So I wanted to talk a little bit about sort of these. So this particular paper that I like quite a bit, that's called the ray interference. So it's sort of the paper itself. It's more about deep reinforcement learning, though I think it applies to deep learning as well. And there's some prior work to this from Andrew Sachs about exact solutions to deep linear models that kind of hints that the same problems might happen in deep models as well. And the idea is what we're showing here is that if you have two tasks that are equally hard, equally complex, and you're trying to learn them together, and there is any form of interference between them, then what would happen is that one task would take over the other. And usually this is decided by initialization. So there's some kind of symmetry breaking at initialization that favors one of the tasks versus the other. And then as soon as one task starts learning, because of an interference, it's going to push the other task down. So the observation is what you'd see is that you actually end up learning the task sequentially. And this happens more often than we think. So even though we have two modes of the data that are equally represented in the data, by chance, by initialization, and sort of due to the interference in this between the data in these modes, you end up learning them sequentially more often than we think. And for deep RL in particular, there's an additional effect where when you do this, what happens is you kind of introduce plateaus in the loss surface. So you end up with this kind of learning curves where you kind of, you learn, you stagnate for a while, and then you learn some more and you stagnate, and like almost like a waterfall kind of learning curve. Cool. So going back to the gradient-based optimization. So I guess sort of the thing that I wanted to highlight is that in normal machine learning, we're relying heavily on gradient-based methods. Gradient-based methods use this kind of tug-of-war dynamics to resolve credit assignment. And what I mean here by credit assignment is basically deciding which weights get to be blamed for which part of your loss. And this is sort of this tug-of-war dynamics is what requires this ID assumption, right? And to me, at least, I think this highlights the fact that normal learning in machine learning doesn't have any form of explicit knowledge composition. So you're not composing the knowledge that you have. You're learning everything simultaneously by having this sort of tension between all the different things that you'd like to learn and trying to find this equilibrium. And whenever you fail to do this credit assignment, that's when you get catastrophic forgetting. So catastrophic forgetting is when you have this tug of war game and some part of the, some opponent is missing. And because of that, you basically forget anything that particular set of examples were supposed to represent. I'm maybe exaggerating a little bit, and I love to kind of go into the details and the nuance of all of this. I'm just trying to do like a black and white picture, but I'm just sort of trying to explain why this can have such a big impact on normal machine learning in general. And the way I see continual learning, and this is sort of how I resolve all of this tension of like the different desiderata and what would happen and what protocol makes sense and what protocol doesn't make sense, is the way I think about continual learning is sort of a study of this credit assignment problem and a study of this tug-of-war dynamics. And then this kind of empowers me with different ways of understanding whether I'm making progress on the question that I care about or whether I'm not making any progress. And I think that's sort of the hardest part in continual learning is you can always tweak the problem slightly one way or another to give you the impression that you're making progress, but you never know whether the progress you're making would be meaningful for the community or not. And usually this stems from the fact that you're not very explicit beforehand of what aspect of continual learning you actually want to study and what exactly you'd like to solve. And yeah, I mean, now I kind of try to motivate a little bit why we should care about continual learning and sort of what are my personal view on why is important to do continual learning. And I wanted to say a few words about sort of where the field is right now. So I think, as a subfield, continual learning is relatively new, but it's been growing really fast. So I've seen, the workshops. So we now have workshops on continual learning, and the number of participants are growing exponentially, more or less, for the last few years at NeurIPS and different other conferences. And I sort of wanted to give for everyone like an overview of what we've been doing in this space. Again, I mean, just kind of highlighting again that, that there are different protocols that you can have in a continual learning problem. All of these protocols make sense. And I think there's been a bit of discussion in the past of some protocols might be not being meaningful. I know that there is this continuous question of whether catastrophic forgetting is something we should care about or not. I think the answer to all of these questions is that all of these protocols make sense. The only problem is that they're looking at different things, and you need to be careful. You need to have this very fine-grained taxonomy of what are the different problems that we might care about, why we care about them, and where we might use the solutions. So there's a little bit of that you need to take into account, and that makes it really hard to compare methods between methods, because different methods, do different kind of trade-offs that are suitable for different aspects of the continual learning problem. The other thing that I wanted to highlight is that I'm going to like branch the solutions into 3 big categories, and this is sort of the standard way of doing it. This is how most papers that I've seen on the topic split the continual learning approaches. But there's a lot of commonality between these things, right? Like sometimes it's really hard to tell whether a method is of type A or type B because it's actually just somewhere in between. And the last thing is, as I mentioned before, there are many subfields that are really close to continual learning, and we have this issue with continual learning and lifelong learning, which are, I think, in my view, almost the same topic. But then you have things like meta learning, transfer learning, domain adaptation, never-ending learning, online learning, and so forth. And they all share a lot of this protocol, a lot of the structure, and a lot of the techniques kind of work in between these fields and are sort of inspired or just sort of taken from different places and brought into the continual learning space. So by and large, I feel that at the moment, what most continual learning solutions are doing, they're trying to imitate sort of the multitask solution. So there is an assumption that what's happening in continual learning is we have a bunch of tasks. Again, you don't always need the concept of task, but it's very handy when you're trying to be pragmatic and explain what you're doing. So if we assume I have a bunch of tasks that you have to see one after the other, the assumption is always tends to be that, well, if I would have all of these tasks together at the same time, and I could do the normal ID learning that we know, and which would just lead to multitask learning, this would be the optimal thing that you can do. And this is sort of what continual learning should be able to converge to, the same solution as the multitask solution. I don't think this is always true, and I might say a few words about this later on, but by and large, this is the assumption. So the idea in most of the solutions is, how can they mimic the multitask solution when you don't have access to all of the tasks at the same time? So in regularization-based methods, and a lot of these works are inspired by Bayesian learning, the big idea there is, well, if I write down the multitask loss that I would like to do, then there's some of these tasks that I don't have access to, like task A and B in this sequence where I have ABC. So what I'm going to do is I'm going to build up a new term, some form of regularizer that will just be a placeholder for these tasks, right? So like in this little animation that I have in the corner is basically the red guy, right? So the red guy is something that I build, and what it's supposed to do is supposed to be an approximation of the task that I don't have, and I can insert this thing in there, and then now I have back my tug of war dynamics. And most of the methods in this sort of family kind of follow this thinking. There's a lot more methods that are not cited here, like VCL and so forth. But basically what they do is they add some form of regularizer, and the regularizer takes care of the tasks that are missing. So this is a first big family of methods. The second family of methods rely on memory and rehearsal. And the idea here is quite simple. It's just saying, okay, I cannot go back to interact with this previous task, but what I can do is I can store some examples from this data, and then I can use those examples. I can rehearse those examples to remember. And there is lots of comparisons with human, and when we dream and all of these kind of things, we have this stage where we kind of in our mind repeating things that we've seen in order for us to consolidate and fully understand what happened. And this is, of course, like a very rich space of things, and then there's like different kinds of ways of approaching this problem. So there's a question of, okay, if I am to store a few examples and I can only store a few of them, which ones do I pick to store? And this question of like compressing the data of the previous task that you have. And then there's also the whole family of approaches that use generative models, where they say, well, I'm not going to store anything, but I'm going to train a generative model of the data that I've seen, and I'm going to use that one, and I'm going to use the samples from that model as sort of my data to train. I wanted to mention a little bit sort of the MBPA model that's there that does something slightly different, and I think it's kind of interesting because it goes back to this question of the multitask solution. So when we do this rehearsal, again, what we're doing is we're trying to imitate this multitask solution, right? We use a little bit of data for the task that we don't have, and to kind of imitate that particular losses. The MBPA does something slightly different, which is what it does is that assumes that what we have is we're going to have a parametric model that gives me like a starting point. And then every time I need to do inference, every time I need to answer, what I'm going to do is I'm going to look in some episodic memory and retrieve examples that are meaningful for that local context. And I'm going to, on the fly, quickly learn an output layer that makes sense for that particular point that I'm trying to do inference for, learn that, do inference with that model, and then throw it away. So there's this idea of like local adaptation. So every time I need to do inference, I need to first do some kind of adaptation to the particular local context, and then provide an answer. And the reason I think this is interesting is because it kind of avoids this question of whether there is a multitask solution. So sometimes you can have a bunch of tasks, A, B, C, that are contradicting each other. So one task tells you to go left, the other one tells you to go right. So if you try to imitate the multitask solution, what you get is you get a system that doesn't perform well on anything, right? Because, well, it's confused and it just doesn't do anything because neither left or right is good, because different tasks tells you to do different things. So MBPA, and you can think of MBPA as basically just taking a lot of inspiration from meta learning and things like that. What it basically does is every time you need to make a decision, it tries to look at the data and it tries to infer what is the current task, what is the current local context, and based on that inference decide what to do. And this way you resolve this tension where, and you can come up with a system that can handle sequences of tasks that are opposing each other, right? Because it does this sort of local inference on the fly. The other thing that I wanted to highlight here in the memory-based method, just to kind of highlight the fact that these things are so similar. So as I said, a bunch of these methods rely on generative models. These are two examples of curl and the hybrid probabilistic model. So their work I was involved in at some point, and they're just sort of different. So the curl is relying on a VAE formalism. The hybrid probabilistic model relies on flows. And this is just a different ways of learning these generative models that give you data. But the interesting thing, in particular, in the last of works in the flow scenario, what can happen is once you have this flow, you realize that you can avoid the process of sampling data and learning on the data completely. And what you can do is you can say, okay, I have the original flow and I have the model that is learning right now, and I want to see that if I take a latent code, push it through the flow, through the original flow, and then use the inverse of the new flow that I'm learning, I want to end up in the same point. And you basically kind of relying on the generative model in some sense, but you end up with a regularization term that is very similar with the first family of methods. And this kind of just shows you that you're sort of on a continuum where you kind of can move from rehearsal to regularization very smoothly. And there's other examples as well, like VCL has corsets and stuff like that, which again, kind of looks almost like rehearsal, and it's like a very continuous space between these two families of methods. And then the last family of methods, the way it's usually split in the literature, is sort of modularity and sparsity-based methods. And the idea here is that you're kind of carving pieces of your model for each of the tasks, right? So you learn task one, and after you learn it, you decide, okay, we know from things like the lottery ticket hypothesis and all of these other kind of studies on generalization and sort of learnability in neural networks, we know that we tend to be extremely overparameterized compared to the size of the solution that we actually need to solve a task. So what we can do now is we can identify that subset of the model that's actually useful to solve the current task, freeze that, and somehow reuse the rest of the capacity to learn new things. And most of these methods, depending on the methods, there are many variations on this, but that's sort of the scheme, right? Is kind of building these modules one after the other, where each module is supposed to map to like different tasks, or if you want, like different distributions, as the distribution keeps changing. I think this is just as a I think this is the family of methods that is probably less explored compared to the other two, but it's probably the most interesting one. So I really hope that in the next few years we're going to see a lot more work in trying to understand the interaction between modularity, sparsity, and continual learning, and sort of learning in non-stationary settings. I think it's a somewhat underexplored part of the problem. And yeah, then like this is sort of gives you like a high-level view of like what are the different methods and what are the way people are thinking about this continual learning problem. And what I wanted to move on from that is to discuss a little bit, okay, what are these methods applied on, and what are the implications of these benchmarks? And as I said, like benchmarks and trying out continual learning, it's one of the biggest problems we have right now in the subfield. So we don't have, we have very well established benchmarks, but there are many problems with those, and problems that basically everyone in the community acknowledges. So it's not like, everyone acknowledges. We've been discussing these topics over and over again every time we meet at any of these workshops. The only question is it's kind of hard to move on. It seems it's a bit harder for us to kind of agree what is the next big thing that we should run things on. But just to give you an idea, so that the kind of benchmarks that we typically use, so these are a lot of time vision-based, just because they're so handy and easy to use. So you can take your favorite vision data set. MNIST, I think MNIST right now is not used anymore. Maybe MNIST is too easy. There's some scenarios where MNIST is still good. But then, you go CFI, ImageNet, OmniGlot, whatever, SDHN, whatever you prefer. And then you split the data distribution into modes. And then you kind of just see the modes one after the other. So this is the sort of split variant, which can be applied to any data set. So you just split along classes, and I mean, you get all these kind of variants of like class incremental and so forth, variants of continual learning. But in big strokes, that's sort of the idea of the split variants of continual learning. And I guess permutedness kind of stands out because it's a task everyone kind of runs on at some point or another, where you don't actually split the data itself into groups, but what you do is you use random permutations of your pixels as new tasks. And the advantage of doing that is you can generate arbitrarily many tasks. So usually when you see a paper that says, oh, I've run this on 300 tasks, it's usually permutedness because it's so easy to generate 300 tasks in a row. But arguably, those tasks might not be sort of the kind of task we care about. There's been some effort in trying to move continual learning sort of in the RL domain, and I've been involved in some of these efforts. But even there, like it's usually done in a very clunky way. So you have things like Atari, and people did this on DMLab, and we've tried to do something like this in StarCraft as well, or other domains. But usually, what you do is you like if you take something like Atari, which is the one that's best studied, you pick these games, you pick a bunch of Atari games, and you put them one after the other. And the issue with this, and potentially issue with the previous benchmarks, is the whole sequence of tasks is it's to a large degree very arbitrary, right? So there is no direct understanding of what is exactly transferable from one task to another, or why you'd even do them in this kind of sequence, right? So this is just sort of arbitrary sequences of tasks that are of variable difficulty, and the focus is the system needs to handle them somehow and needs to be able to learn them. And then once you've set up your benchmark, whatever it is, the typical plots you would do. So I took this out from EWC, but most papers would end up making plots like this. Is you're looking at the average performance on all the tasks, and you have that your method is doing better, or you're specifically trying to focus on catastrophic forgetting. And I think this is sort of one of the main criticisms that people usually have to papers in continual learning is the over-reliance on catastrophic forgetting. So the first thing that everyone looks at is, like how much does my system forget when I learn new tasks? And I just sort of want to re-emphasize that actually this is not the only objective of continual learning. So at any point in time, there was never said that, okay, continual learning is about resolving catastrophic forgetting. Continual learning was always about, resolving catastrophic forgetting in a way that gives you forward transfer, and you have a fixed size model and all the other desiderata that I've enumerated at the beginning. But by and large, catastrophic forgetting seems to be the thing that kicks in first. So it's the thing that you see immediately as you start to running on a sequence of tasks, and somehow most papers and most of the community kind of ended up focusing on solving this catastrophic forgetting problem, in the expectation that we can solve this and then we can move to the next one. But as I said before, I think this is extremely problematic because this desiderata is actually in tension with each other. So there's no sense in which you can say, okay, I've solved catastrophic forgetting, this is solved, I'm going to fix this, and I'm going to start solving the other bit, and kind of just combine the solutions as we go along, because there's no combination. Like when you start combining them, that's when you start needing to do some kind of trade-off. So you need to allow yourself to forget some in order to learn faster, or something like that. Okay, so this is sort of usually the kind of plots people do. Sorry. And then you can I guess you can then try to plot this is like a set of methods, and you can try to plot these models and see sort of what they do. And I think I'm going to explain the table a bit later, but I think one thing that comes out at the moment from most of these continual learning methods is that we've become pretty good at dealing with catastrophic forgetting, right? So performance is there. It sometimes feels it's kind of neglected in the field, but sometimes it feels like we're losing a bit of performance, or how much generalization. So we're losing some plasticity, it seems, in practice. Is usually not much, but probably it's still extremely important. But forgetting by and large is solved. On the other hand, if we're trying to measure any of the other desiderata that we might care, so in particular here we're also looking at forward transfer, we notice that basically any method that does well on forgetting, it does worse on forward transfer. So it's a direct trade-off. At least in the methods that we have right now, it seems we're doing a direct trade-off between speed of learning and sort of the ability to remember, which is actually not what we wanted, right? So the intuition that we started, or at least the story that I was trying to tell you, is that in continual learning, the whole point is you build on the knowledge that you acquire knowledge from one task to another, and you protect that knowledge, so you always remember what you've learned. You've learned a bunch of skills, you remember those skills, and then when you see a new task, you can build on those skills, so you can learn faster. And it feels like exactly the opposite. It happens. Just because you're maintaining the skills, you can't learn faster, and you can't learn as well either. So you're basically sacrificing everything in order just to remember these things that you've learned. In the minutes that I have left, probably roughly something like 20 minutes or so, I wanted to start discussing of like a way forward maybe for this. So this is sort of a benchmark that we've recently worked on. And maybe a way of thinking of the problem. So I think what's important when you're trying to set up this kind of continual learning benchmarks, it's important to have an understanding of what is it that you're doing, why you're putting this task together, what is the goal, what is the best you can hope to achieve, what is the worst you could achieve, and where are the methods that are out there already. And in particular, when I was thinking about these things, I came up with this story that we call the distractor problem. So the idea is that whenever you learn in a sequential way, and assuming we have tasks just to make things easier, the paper is actually on archive. The slide is a bit old. You have a sequence of tasks, A, B, C, D. And one thing that happens more often than not is that a task starts behaving as a distractor. And what that means is that if I'm looking at a transfer, the like naive transfer between A, B, BC, and AC, I see, I think I have a plot for this just to make it a bit clear. You get sort of one of these kind of transfer matrix where you say that, A is helpful for C. So if I learn A and then I learn C, I tend to learn C much faster. A might be or might not be helpful for B. I think that's a little bit less important. But then B is harmful for C. So if I learn B and then learn C, I actually learn C much slower, because somehow the task B and C, they don't like each other, right? They tend to use different features. They tend to interfere with each other. So if you pre-train on B and fine-tune on C, you have this negative transfer. And the idea in this work, in this distractor problem setup that we're setting here, is that we want to use this transfer matrix as a way of talking about the similarity between tasks. So this is a very hard problem in the field, and there's different papers on it and different views on it. But in general, when we have two tasks or two data distributions, it's really hard for us to talk about how these two distributions are related. You have very simple metrics like KL or whatnot, but those are not necessarily informative, and it doesn't really tell you that, okay, if I have a particular model, how much would this model be able to exploit the common structure between A and B? So this is something that people talk a lot about it. So the causality seems to be a tool right now that people tend to like to use for this and say, oh, if there's like common causal structure between A and B, then this is related, and sort of that common structure tells us what is the commonality between tasks. But I would argue that with the models that we have right now, so if you'd end up training a ResNet on those tasks, this causal graph is actually not informative at the moment, because the way ResNet learned the solutions is somehow not relying directly on the causal graph. So you need to go deeper and build a solution that directly relies on the causal graph, which it's sort of a different direction, which is also extremely interesting. But at the moment, for the architectures we tend to use in practice, the architectures that really do tend to perform well and are generic enough to apply to sort of data for which you don't have very explicit prior knowledge of exactly sort of where the data comes from, it's really hard for us to tell the similarity between tasks. So the idea in this distractor problem is, okay, just to use the transfer matrix to kind of give you a sense of similarity. Now we have this transfer matrix. Now what we can do is we can create a sequence where we can look at distractors. We can add a distractor in the sequence, like B in this particular case, based on how things happen when they transfer, and then say, what we would really like is to have this kind of magical continual learning solution that will be able to learn A, B, C, and it will be able to mitigate the interference that B induces. And we're not even looking for like the best case scenario here. So we're thinking about like a realistic target, which would be like, what I want to do is learn A, B, C, and then C as fast as if A was the task I've pre-trained instead of B. right? So you could have compositions of transfer. So it could be that if you had, you know, many tasks before, it could be that you can compose how much forward transfer each one has. But for now, we're just setting as a target, like transfer as much as sort of the best of the previous task. And this is sort of just a target for us. And we wanted to do this sort of in a realistic scenario. So we've made this paper. So now you have the link that should have been on the previous slide as well. So we built this continual meta world, or continual world, and it's basically what we wanted. We wanted something super pragmatic that people can use. So we went with a benchmark that's well established, meta world, and it's cheap enough that people can easily run, but sort of still interesting enough to see some interesting structure. In particular, still interesting enough to kind of see this kind of destructor behavior. So we're trying to move away from things like Atari, where like it's actually quite, the tasks themselves are a lot more challenging, and sort of the transfer matrix is a lot more noisier. And what we do here is, you know, you compute the typical metrics, so you can do average performance forward transfer and so forth, and for getting. For forward transfer, you just sort of look at the area under the curve, and you're asking yourself, how much faster am I learning now if I did pre-train? And then you can compute sort of a transfer matrix like this, and use that transfer matrix, and now you can construct the sequence, and now you can construct kind of like a reference transfer, which is, if you had a distractor, ignore the distractor and tell me how much you'd have transferred if you didn't have the distractor in there. So this is sort of what this RT number is. So again, as I said, this is not an upper bound. So it is possible for continual learning systems to do even better than this, but it is like a reference transfer. It is like a target for us to see whether we can even achieve this. And for the data set we have, this gives you some numbers, some 0.4 in this particular case, 0.46. And the idea, what we've done in this paper, is we just took existing methods, we ran them. So this is a table you've seen before. And what you can see is that at best, you can do as well as not using any continual learning system if you're just looking at forward transfer. And that is 0.2, so about half of what this reference transfer would do. So that is still heavily, heavily penalized by these distractors. So I think this is kind of just tells you, like, okay, what are the difficulties in sort of the systems that we have, and particularly like now, because we're focusing on this idea that we want a continual learning system that is able to build on the knowledge that it has and kind of use that to learn faster. It kind of shows you that the solutions we have so far, they're not doing that. So they're good at dealing with catastrophic forgetting, which is fine, but they're not dealing with catastrophic forgetting in sort of this kind of way that allows you to actually exploit whatever you remember in order to learn more efficiently things that come after. It actually does the opposite. So almost all solutions to catastrophic forgetting that we have now forces you to pay a continual cost. You know, it's like they many times it's a computational cost, but it also like prohibits forward transfer in a direct way. And this is sort of what you can see from the table. So this was, I guess, a discussion about sort of the weakness of evaluations, especially sort of the original kind of benchmarks that we used, which were kind of random sequences of tasks where, you know, you'd run continual learning system, you'd focus on catastrophic forgetting. There was a note I wanted to make again. So why wasn't this such a big thing in the past on the previous benchmarks? And I think part of it is, if you take something like permuted MNIST, so if you take some of these tasks, it's actually completely unclear whether there is anything to transfer at all. So then, you know, even if you compute the forward transfer number, that will be close to 0, and it will be close to 0 for all methods because there's nothing to transfer. So then obviously your eyes go to catastrophic forgetting, where you see a huge gap and kind of dominates the whole thing. So it's sort of important to have the right benchmarks that highlights the part that you'd want to explore. And again, as I was saying before, this is not saying that the old benchmarks are not good or the methods that we have are not good. It just depends on what question you're asking. So the particular question we were asking here, which is remember things in order to reuse them later, that's not being answered correctly at the moment in continual learning. The other thing I wanted to highlight quickly before I finish my presentation is something about another issue with continual learning, which is sort of in my view, reliance on overparameterization, and it's sort of a kind of a thought question whether this is a good thing or not. So just briefly, what we've done here is we took many of these kind of typical benchmarks like CFAR, mini emission, and so forth. And then we look to see, so we use this mode connectivity. So some of you might know, there's this idea of looking how two solutions are connected to each other. So this mode connectivity stuff. And we're looking to see how the multitask solutions, which we assume are the best thing you can do in continual learning, whether they're mode connected and how are they mode connected. And what this paper kind of, like what this experiments kind of find is that for most of these benchmarks, all of the solutions that multitask give you, they're linearly connected. So another way of phrasing this is basically, if I learn task 1 and then I learn task 1 plus task 2, I find a solution for both tasks. And that solution is within the region where the second order Taylor expansion of the first task holds. And then this is interesting for two reasons. One, it basically says that regularization-based methods, which in the literature, if you kind of skim through recent papers, are kind of seen as being inferior to rehearsal-based methods. They technically can do as well, because the core, they're seen as being inferior because they're making these very strong assumptions about, okay, I'm going to take a second order Taylor. I'm considering that the posterior is just a Gaussian. So these are technically seen as very strong assumptions on the structure of the loss surface. It seems these assumptions are good enough, right? Because multitask doesn't take you somewhere where these assumptions don't hold for most of these data sets. So this is one observation. But the other observation that I think to me is also important is the reason you get this kind of property is because we're in an extremely over-parameterized regime. So somehow the over-parameterization comes into play. And if you reduce the parameterization, like these things don't happen as well. And this is sort of a very generic thing, right? Like if you take ResNet and ImageNet, that model is over-parameterized. And over-parameterization seems to be key for a lot of the results we have in deep learning. But the question is whether this is something we want to heavily rely on. So in particular, if you think of a lifelong learning scenario where the distribution keeps changing, and whether you're trying to remember all this kind of previous distributions that you don't see anymore, you might quickly end up in an under-parameterized regime, or you can end up in a regime where you don't have this over-parameterization to help you. And the question is, what happens then? Do all the methods that we have that seem to be doing so well, are they all relying on this assumption? And actually, if we push them in an under-parameterized regime, will they all break? And do we even need to address this problem? Is there a way of addressing it without making our system under-parameterized? Sorry, this was a last slide on the same thing, but it basically just showing that you can use this mode connectivity, and it's very reliable, and this sort of works as well as any other method for the typical tasks that we see. So this is more saying something. This potentially is saying more about the benchmarks than saying about the methods. It's basically just saying, the benchmarks that we have, they're such a nature, and the model we use are so over-parameterized that actually this kind of very simplistic assumptions like second-order Taylor approximations, Gaussian posterior, stuff like that, they seem to hold perfectly. For even after we see, just to be clear, even after you see like 20 tasks in a row or like 50 tasks in a row, you still can do a second Taylor of the first task, and everything is within close within that really region where this approximation holds. And now I hope I'm not over time. So this is, I went through a bunch of works, but there's a lot of people I worked with. I just wanted to, it's been a really hard year now, 2 years almost for everyone. So I just wanted to give a big thank you to everyone I've collaborated with in the last, 2+ years. And I'm sure there are many people that I forgot, but none of the things that I managed to do would have happened without the help of others. And just wanted to say thank you, and whether there are questions about the presentation. Yeah, so if anyone has questions, do please write in Slido. So that's sort of the main mechanism for us to see the questions. So put your question in Slido, and yeah, I'll be able to. Okay, so I can start looking at the questions. So the first question appearing here is, are we going to see more formally? Sorry, I need to make this a bit bigger for myself so I can see. Okay, so are we going to see more female presenters and people from other underrepresented groups? Is this particularly related to the workshop? So if you look at workshop, I mean, we already have the list of the speakers, so you can see directly who will be speakers. In terms of female presenters, we've always strived to try to be as balanced as we can, both for this workshop, but also for most of the events that we've done in the past. And I think this is a tendency now in the field as a whole. It's a sort of a slow process, and it takes time to get there. But definitely, I think almost everyone I know of organizing all kinds of events, even like the big conferences, for them, this is a very big topic and something everyone pays a lot of attention to. Cool. So this was the first question. For the second question, what is differentiating point between continual learning and lifelong learning? So depends on who you're talking to. So in my mind, I do feel like these are kind of asking the same questions. The typical answer that someone would give you is lifelong learning has a bigger emphasis on a really large number of tasks, while continual learning experiments tends to be with a smaller number of tasks. As far as I know, this is sort of the big thing that maybe people bring up, but I think it's a very superficial difference, and actually we all kind of care about the same regime. So yeah, hopefully that helps. How important is graceful forgetting in CL system? What methods could help? Yeah, so this is a very good question. It's something that people have been discussing. I've been thinking about it a long time, for a long time as well. I do think graceful forgetting is really extremely important for CL systems, right? It's a way of kind of controlling this trade-off between forgetting and transferring capacity and all of these things. The issue we've had in terms of, like, if you just look through the literature and you try to find papers that are talking directly about graceful forgetting and providing methods that deal with graceful forgetting, you won't find many of them. And the reason for that is, and from my personal experience, we've actually came up with a method for graceful forgetting, and then we tried to use it in one of the existing benchmarks, and it just doesn't make a difference. So I think part of the problem is we need to have the right settings for us to exploit this graceful forgetting. When we go to a really large number of tasks, we end up using something like permuted MNIST, and I don't think that is the right problem. So we need a much more natural setting where you can have hundreds, maybe thousands of tasks that are difficult enough and interesting enough for you to use, like, modern deep learning tools and kind of deal with this graceful forgetting problem. But by and large, it's super important. Everyone agrees. We just need to find a way that it's much more practical to actually do experiments on it and publish works on it. But yeah, it's a very important theme for continual learning. Okay, so for the next question, are you familiar with the applications of continual learning in industry? So I'm not that familiar, and I would be definitely interested to understand more. Like, so the issue with continual learning, I think, in industry, or at least my understanding, is that we don't necessarily have tools that work well enough that would be applied. We definitely know setups where it would, like, naturally be a solution. Like, we know, for example, that whenever you have, I don't know too much about recommender systems, but for different various systems, you have data keep coming in, and what happens more often than not is, the solution that they have is thrown out, and a new model is to retrain on the old data plus the new data, and you keep doing this regularly. And this is kind of expensive and computation intensive, but you can parallelize it, run it in the background, and a lot of big companies do this for a lot of things that are out there. And we'd really like not to do that. We'd really like to just kind of continue training the system that we have. There's also people who try to just fine-tune the system, as far as I know, and there's good reasons for that. If you just fine-tune it, you kind of lose performance. So you really need to throw the system away and retrain it from scratch. I think it would be nice to have a continual learning solution that really, can work in that setting. I don't know whether they're there yet, but I think the issue is having like a benchmark where we as researchers can work on, but where the solution can directly be applied in industry, because I think it's kind of hard to kind of motivate the researchers to work directly on applied problems that are, sort of hidden under the hood. And if they work on that, again, that's something you publish on, and people would not know you work on. So yeah, I think we're breaking that barrier, coming up with a huge benchmark that's interesting, that is approachable, but it has like direct application in industry. I think that could boost the field quite a bit. And there are people thinking about this, and there's some proposals out there, but don't think there's yet one that kind of took over the field and everyone is saying, okay, this is the challenge, this is what everyone should be doing. Are there other approaches to detect distractor tasks? So, I mean, that's a good question. I think the way we define distracted tasks is through this transfer matrix. And this is because we needed some kind of similarity metric. At a high level, conceptually, what we're talking about is if there is, we're talking about similarity between tasks, and we're talking whether there is, a task that is not similar to another, that would kind of induce the distractor. But yeah, pragmatically, I think transfer matrix, to me, in my mind, is the most reliable way to detect whether there is interference between two tasks. There are some works on task similarity out there, but again, they tend to make some kind of strong assumptions. There is even benchmarks that are using sort of causal graphs to kind of define the relationship between tasks, and then you can use that and define sort of what the distractor is according to that. But the question is, so my experience is when you train systems, like the kind of transfer, the kind of learning you see depends heavily on the architecture you use, the optimizer that you use. It's not just about the data. So I'm a bit skeptical about sort of similarity metrics that don't take into account the model and the learning process when they compute the metric. So I don't know how reliable they are. Okay, next question. Extending the previous question, what about online learning? So online learning is very related as well. There's a difference, again, I think it's a difference of communities, a difference of focus. So a lot of online learning work is done in a, a lot of online learning work is being done in a more of a theoretical framework. People really care about bounds there, which is something we don't really care about continual learning. And in the online literature, a lot of time people really avoid using systems for which you can't compute regret bounds and stuff like that. So they tend to use like linear models and other kind of, so that's, in my mind, that's superficial, but it is a difference. The tools that they use, the community, the kind of papers you can write, the kind of reviewers you can expect, right? So it's about theory, it's about regret bounds and stuff like that. While continual learning is not that much about that. But the other thing is, forgetting is not that big of a theme in online learning. There is ways of formulating the online learning problem to have forgetting in there, but it's not sort of the mainstream one. But otherwise, there's a lot of similarities. So you can take even algorithms like EWC, and you can find some of the roots, or you can find a lot of similarity between these algorithms and some online learning algorithms. So that definitely there is a lot of commonality between this, and I don't think it's acknowledged all the time, and I don't think we have enough online learning experts working in continual learning or enough continual learning people trying to do online learning. So it would be really nice if we get more of that. Okay. Okay, so could the distractor problem pivot to be a cybersecurity issue in non-deployed CL system? Yeah, the attacker intends to disrupt the running CL model by. Sure, it could be exploited that way. That's a very interesting and nice way of phrasing this. You could definitely, like, I mean, assuming that a system, like if you are to think about pragmatically nowadays, assuming that a system is continuously fine-tuned, which is the most likely thing, you can definitely exploit how you can, how you can affect locally the distribution of the data that the system is seeing, such that you kind of make it forget arbitrary things from the past, or basically even catastrophic forget and breakdown. I haven't seen any work looking at this directly and discussing sort of how you would exploit this. I think it's a really cool perspective. But yeah, definitely, it would be nice to see. I mean, I guess now here, like, there is a lot of strong assumptions, right? Like, you need to make strong assumptions about how the system learns, whether it learns continuously, whether it's a static system that throws data away, stuff like that. But yeah, if you assume a system continuously learn, you can definitely play this game. And this might become a really interesting problem for things like self-driving cars and so forth, if they tend to adapt, after, adapt to the driving that you do and stuff like that. Then you can ask, okay, how can you break a system like this? That's a really good point. Cool. So I think we don't have time for questions anymore. So I want to thank everybody, and I'm on Slack. So if you have questions, yeah, I'm happy to keep answering them on Slack.